This is a neural network, and today we are going to build one completely from scratch. That means no TensorFlow, no PyTorch, or no machine learning frameworks. Just Python functions, NumPy, and a bit of math. We'll start with a single neuron, gradually combine them into layers, and eventually build a fully functioning artificial neural network that can actually learn. Then, to see how well we have done, we'll train our neural network on the famous iris data and compare its performance against a neural network built using modern machine learning libraries. Before we move on with anything, we need to first get our data. And like I said, we're going to use the famous iris dataset. It's like the hello world of machine learning. It has 150 flowers or rows, each with 4 measurements, and we need to classify them into 3 types of iris flowers. So to get that dataset, they have made it really easy. So let me just show you. As you can see by the inputs, how easy it is to load the iris dataset. First, let me just explain what are these inputs. NumPy is to do the maths we are going to use. It handles all the matrix operations we need. And then we have load iris, like it says, a helper that gives us the iris dataset. And the train test splits. It splits our dataset into training and testing paths because that's what we need when we're working with machine learning languages. And import time, it measures how long training time takes. Now, moving forward, what we need to do is we need to load and process this iris dataset. And we are going to build a function for that. As you can see, I'm using this load and process data to load our iris data, then split them into our features and our target, where X are the features we need and Y is the target or the results we need. So next we used min-max to normalize our data. So if we have any outliers, we'll just kick them out using min and max. Next we have one-hot encoding, where we use one-hot encode to encode our labels. This is like saying this is a rose versus this is not a rose, it's a tulip. That's what we are doing here. Then we are splitting our test and train data. We are splitting 80% to train the data and 20% to test the data. Training data basically is what the network learns from, and testing data is what we use to check if the actual learning happened. And then we return the test and train. Moving forward, we have to initialize the parameters. Like every neural network has weights and biases. Think of weights as the strength of the connection between two neurons, and biases as the threshold that decides if a neuron should fire or not. So to do that, we are going to define another function, that is initialize parameters. So this is how we initialize the parameters. As you can see, we have divided it into weights and biases, like I said. So that's what we are doing here, initializing our weights and biases. As I showed in the beginning of the video, the diagram, where we have input, hidden, and output layer, what we have to do is input layer, where we input all our features, like the 4 features we are going to use. And then hidden layers are the layers that actually do the work, the processing, where they calculate weights and biases. And output layer is where we show the output. So in the input layer, we already know we are going to input our parameters or features, right? In the hidden layer, we have weights and biases plus an activation function. And that activation functions is exactly what we are going to build here. Now, activation functions are like the decision maker. They decide if a neuron should be on or off based on the input it receives. And here we are using 3 different activation functions. So first, ReLU. This means basically if it's positive, keep it, and if it's negative, make it 0. It's like a filter that only lets positive numbers through. Whereas ReLU derivatives, they are like, if it was positive, the slope is 1, else 0. We need this for learning or backpropagation. We're going to talk about backpropagation later on. So there, you'll understand what this is used for more. In Softmax, it just basically converts numbers to probability that sum to 1. It will give 3 different probabilities for our 3 different output, and the one with the highest probability will be our output, looking at the features. So that is what this is used for. Next, what we need to do is the loss function. Now, loss function, it measures how wrong our network is. It's basically a mistake meter. The higher the number, the more mistakes the network makes. To do this, we are using Cross-Entropy loss. And this here calculates our loss. So imagine you're playing a guessing game, and if you're confident, say 90%, and you're wrong, that's a big mistake. But if you're unsure, 50%, and you're wrong, it's not as bad. Cross-entropy captures exactly this in perfect harmony. So this will help us see the mistakes of our neural network. And then we have forward propagation. This is when our network moves through input layer to hidden layer to output layer. So to move that, what we are going to do is create a function called forward propagation. And as you can see, we have the forward propagation right here. What it does is when you input a number that comes in 4 measurements, as we talked about, our iris data has 4 different measurements. They get multiplied by weights and biases, initialize parameters, and then ReLU, this decides which number passes through. And another multiplication and addition happens, and then Softmax, this converts converts them into the final numbers to probabilities, and the one with the highest probability will be shown as the output. Now, after we get the output, our cross-entropy losses checks what our losses were or how wrong we were, and then we have to send it back to fix the parameters, weights, and biases, because our neural network is actually thinking and it knows if it makes a mistake, it needs to change something so you can get a better answer later. So that's why we are going to use backpropagation for it. Like the name suggests, it means going back and fixing things. Backpropagation also calculates how much each weights contributed to the error and adjusts them accordingly. Now let's just do it first. So as you can see, this is a backward propagation function, and let me just explain this. So imagine you're playing darts and you miss the bullseye. Backpropagation is like figuring out how to get the target. This asks us questions like how far were you from the target? Did your wrist angle cause the miss, or did your elbow position cause it? And how should you adjust next time? And this becomes an update. The chain rule from calculus is used here. It's like the blame game, where each part of the new network gets a share of the blame for the mistakes, and then they fix it. And to fix the mistakes, that's where we update the parameters. We initialize the parameters here, but now after the backpropagation, after we know the mistakes, we have to update the parameters so we know we don't make the same mistakes next time. Now, as you can see, we have this. The learning rate is the rate at which we learn. So now that we know how much each weight contributed to the error, we update to reduce the future error. And this is what we call a gradient descent. And this is where learning rate comes in. Think of learning rate as the step size. When you are trying to find the bottom of a valley in the dark, take a big step and you might overshoot and miss it. Take tiny step and it takes forever to get there. So we need the exact right kind of learning rate. And that's what update parameters does. Now, this is where our training ends. And after the training, we need to make predictions and check how accurate our network is. And this two function is what we use to predict and see how well our neural network performs. Predict is like asking the network, what do you think this flower is? And it gives you its best guess. And accuracy, this is like grading the network's test. What percentage of answers were correct? This is basically an exam, and this is the grade the teacher gave us. So before testing the predict and accuracy, we need to actually train that. We have written all the codes that are needed to train the dataset, but we haven't made them come together. So this is where we are going to make them come together. As you can see, we made the function train neural network. This is where the network actually learns. What we do repeatedly is make the prediction forward pass, then calculate the loss, as you can see, cross-entropy loss, and then figure out what went wrong, and then use backpropagation to send everything we got wrong back. And then using that result, what we do is update our parameters so we get a better answer next time. And this time we are using epochs. Think of each epoch as one round of practice tests. And after the round is over, we throw the dart again, forward propagation, you see how far you were, we see the loss, and then you figure out why you missed, and then you adjust your aim, try it again. After thousands of rounds of practice, you will be much better at hitting the bullseye. This is basically what we are doing here. Now we need something like a conductor for an orchestra. We need to bring everything together and make sure they all work together. And this is where the main function comes in. As you can see, we made all of them come together, and this is where the final magic happens. And to finish it off, what we are going to do is, if file name is main, then start main.py. So as you can see, neural network isn't very hard. It's just making a mathematical algorithm go back and forth and make itself learn. So let's test it out and see how it compares to our neural network that we built from MLPClassifier, standard scaler, and then see which one does better. So let's run it, and we cannot run it from here. What we need to do is go to terminal and then activate our virtual environment. And also don't forget to install Scikit-Learn. So this is Scikit-Learn is sklearns here. I already have it, so that's why my requirement already satisfied. It might take a little time for yours. So next, let's just start with the Python main.py. It's going to take a while to get our results. Till that time, we're going to open another one, and then we're going to do the same for Python compare.py. As you can see, this was a lot faster to train. So this, all you need to focus on is this modal summary. The framework is Scikit-Learn. We use the library MLPClassifier. And for the architecture, we use 4 input layers, 8 hidden layers, and 3 output layers. And accuracy was 100%. And total test sample, like I said, 150 flowers. And here we got the result as well. And this is the epoch that we ran. And each time the epoch ran, you can see our train loss going down and test loss going down. By the end, it is 0.12 and test loss is 0.12. 0.11. But as you can see, the accuracy is 96.67 and the training time is 0.1220. We only use frameworks like Python and NumPy and we coded it from scratch. So architecture is the same as the other one, as you can see, but the accuracy is better when you use a library. So let me know in the comment video what I should make from scratch in the next video, and I'll see you there. Happy coding, keep coding.